Okay, so this video is going to cover Cepheid variables, the idea of luminosity and observed intensity, and how we use those things to use Cepheid variables for distance measurement. Okay, so we need to talk about what luminosity and observed intensity are first in order to do this properly. So the idea of the luminosity of a star is that it's equivalent to its total power output, the total amount of power released by the star, so total energy per second. And that's obviously going to depend on things like the temperature of the star. The higher the temperature, the higher its luminosity will be. And the size of the star. A bigger star, again, will have a higher luminosity. These things are going to be important when we talk about the Hertzsprung-Russell diagram in a separate video as well. But for the moment, let's just think about them in terms of distance measurement. So, just for reference, so the Sun has a luminosity of 3.8 times 10 to the power of 26 watts, which is tremendous power output, obviously. And what happens is as the light spreads out from the star, the power is spread over a larger and larger area. And so that means that the intensity of the light from a star will decrease as the distance from the star increases. And it's often illustrated with this diagram. So if we start with the star as a sort of point-like object here, and we go a certain distance away, the light coming in this direction has spread over this area. And if we go further away, it's spread over a larger area. And if we say those two lengths are roughly equal, then we can divide this area up into 4. We can see that basically, if we double the distance away from the star, then we're going to reduce what we call observed intensity by a factor of 4. Okay. Now, the syllabus says that you have to have a qualitative description of how we use Cepheid variables for distance measurement. I'm not going to actually do any calculations here, but I think it's useful for you to know that there is a formula that links these things together. So qualitatively, we need to know that the observed intensity, that's what we see on Earth, is greater for a star with a higher luminosity. That makes sense. Okay, the more power it's giving out, the more intensity we're going to see, and it's also greater for a star that is closer to us. Okay, that means the light is spread out less. So those two things make sense, and that can be expressed by this equation that the observed intensity I is equal to the luminosity, the total power output, divided by this 4 pi r squared. And for any of you who are mathematical, the 4 pi r squared is the surface area of a sphere, right, with a radius r that's corresponding to the distance from the star. And if you think about it, that sphere is the area that the power is spread out over. You don't really need to appreciate anything about that equation except, right, that as in all equations, we've got 3 variables there, I, L, and r. The 4 pi is constant, so we know what that is. If we know two of those 3 things, we can work out the third one. So if we knew the intensity, the observed intensity, and the luminosity, we could work out the distance from the star. And that fact's going to be critical for explaining why Cepheid variables are useful. Okay, so let's just talk about this idea for a second of what we call standard candles, because Cepheid variables are an example of this. So the problem with using this equation is that we need to know 2 things. So if we're trying to measure the distance, we need to know both the observed intensity. That's easy. We just look at the star. But we need to know the luminosity. That's a lot harder, knowing what the power output of the star is. Now, we can have some idea from the colour of the star, as we'll see from the Hertzsprung-Russell diagram. That gives us some idea, but doesn't necessarily tell us how big the star is, which also matters for what its luminosity is. So that's the trick. If we can find a way to work out what the luminosity of the star is, then the combination of the observed intensity, which we can easily measure, with the luminosity, will allow us to use this equation to work out distance. So that's what the whole thing's about, okay? And this idea of a standard candle is that for these things called standard candles, we know what the luminosity is. And the Cepheid variable is the example you need to know. Other examples of standard candles, if you're interested, would include things like type 1a supernovas. You can go and look up what those are. Things where we know what the luminosity is going to be. Okay? So, I'm now going to talk you through what a Cepheid variable is, and then we're going to do a step-by-step of how we can use the properties of Cepheid variables to get to the luminosity of the star, right, the total power output of the star, and use this equation. Okay, so a Cepheid variable is a star that shows a luminosity variation. Okay, so the amount of power it's giving out changes over time. In fact, these stars tend to exist as they're coming off the main sequence in the Hertzsprung-Russell diagram. So they're slightly unstable, and they get develop this oscillating behaviour. You don't need to know anything about the reasons for this, and in fact the reasons for it were unknown for a very long time. Okay, but what you do need to know is that if you've got a star that's high average luminosity, so it's got a very high power output, then the period of variation for that star is long. So that's this top line here. Okay, and if you have a star with a very low average luminosity, it has a shorter period of variation right here. These curves, by the way, of the change in luminosity are actually called light curves. Of course, we can't directly measure the change in luminosity of the star. What we can see is the change in observed intensity, but the important point here is that the period will be the same for both of those. So whilst we might not know how the luminosity is changing, we can measure the observed intensity. That will give us the period of oscillation of the luminosity as well. Okay, so that's what a Cepheid variable is. Here's how we use that to work out the distances to any Cepheid variable we like within a reasonable degree of accuracy. Okay, so step by step. I'm going to put that equation there again just because we're going to need to refer to it a couple of times in terms of using it to work stuff out. We're not actually going to do the calculation, we're just going to look at what variables we know. So we need basically a way of what we call calibrating the Cepheid variables. So what we need is a distance measurement that doesn't rely on luminosity, and the one we know about is parallax. Okay, so if you remember that the parallax method, again, we'll have a separate video for that, is just that from observing the shift of a nearby star against the background of very distant stars over 6 months, we can tell how far away it is. Okay, so big shift means close, small shift against the background of stars means further away. So we've got a method of measuring the distance for this star. We can look at the observed intensity as well, okay, and we can also look at the light curve, right, to get the period of the luminosity variation. We can't get the luminosity directly. So those last two things are both just observable by using the light arriving on Earth. That's critical, okay? So for these stars, okay, we can use the equation to work out luminosity because, as you can see, we've measured the distance r using parallax, and we've measured the observed intensity. So we know two of these things. We can work out the luminosity for these nearby Cepheid variables. In fact, there was a satellite sent up called Hipparcos in 1989 that did this. It measured 273 nearby Cepheid variables to kind of confirm these ideas to a very good degree of precision. Okay. So what we then do, as we often do when we've got some measurements, is we plot a graph for all the Cepheid variables we've found of luminosity, in this case we're going to put it on the y-axis, against period. Okay, and what we find is there's a relationship. Now I've drawn just a straight line on here, so there's a correlation. In reality, of course, the points are going to be scattered about this line. I should also note that I've not drawn any scales on these axes. They are not standard scales. The spacing is not even if we want to get a straight line. So if you get given a period luminosity graph in the exam, you will probably find that the scale is slightly weird, possibly in both directions. Just be careful and watch out for that. Okay, so what we then do is we extrapolate. We make the assumption that all Cepheid variables in the whole universe follow the same correlation that we've discovered for our nearby Cepheid variables. This correlation between the period of luminosity and the average luminosity. Okay. Then we can start looking at some Cepheid variables outside our parallax distance range. Okay, and this is what we do. We do the same things. We can't measure the distance this time because parallax has got a limited range because we need to measure very small angles. Okay, so we measure the observed intensity and we measure the light curves again to get the period of the luminosity variation. Now here's the critical thing. Now we know about the correlation. Right, both those two things are still from observing the light arriving on Earth. We use the graph that we've got for our correlation to read off the luminosity from the measured period. So we take this second measurement here and we go bump, bump. This is our measured period. That means the luminosity of our star is here. So now we know the luminosity from this read off, and we know the observed intensity from our observations on Earth, and then we feed those two, I and L, into our equation, and that means we can work out R. If we know two of the unknown things, we can work out the third one. So there's the step by step. As you can see, it's quite a lot of steps to explain it in full detail, to explain how to use Cepheid variables. In terms of answering a question, I mean, that's probably a lot more detail than a 6 marker would need, but you would certainly need to be able to explain the problems that you usually have with trying to use these distance measurements, and how the Cepheid variable allows you to determine the luminosity of the star. So in particular, this middle section here, okay, that you observe the nearby Cepheid variables, plot the graph, and that lets you read off the luminosity for any Cepheid variable, if you make the assumption that they all follow the same correlation. You may want to watch the last section back again and just make sure you're happy with all the steps, because there is a lot of stuff in there, but hopefully that helps you understand how Cepheid variable distance measurement works a little bit better.